So our next speaker would be Douglas Wilson, presenting improvements to GHC's parallel garbage collector.
Hello.
Hi.
There we go. Hi, everyone. I don't have a video, so let me just share my screen. All right, is that working? Yep, nice. Okay, hi, everyone. I'm Douglas Wilson. I'm a Haskell consultant with WellTyped, and this is some work that I did earlier this year to make the garbage collector work better. There's no Haskell in this talk, unfortunately, but there's some. I try not to get into the C too much. So I did this summer 2021. It's in GHC 9.2. Most of the work's in Linux on AMD 64 architecture. So we're going to be talking about things that they're different on different platforms. So I'm a little bit less confident about how much better this is in. Yeah, it was the southern summer. Yeah, it was the southern summer. So what we're doing is changing the way the cross-thread synchronization works. And it in particular reduces the CPU times for Haskell programs. I'm going to show some measurements of the improvements, then talk about just what changed and some other experiments. So this is a chart of building the Cabal library with GHC. It's a really simple test to run when you're working on GHC because the dependencies are guaranteed to work. Now, the most interesting, well, I think instructions here. So this is the instructions as measured from perf. You can see it's 7.5 times 10 to the 11 with the baseline. And then with my changes, which I call them no spin GC, it's pretty flat. So we've got cores on the x-axis. And then these are different measurements that have come out of the compiler. All of these measurements they're over like 6 samples. And they're all done on my laptop, which is a Zen 3 AMD, and with 8 cores, 16 gigabytes, hyper-threading on. And then I work everything in a 12-core CPU set. So where you see 16 here, this is approximately running with 16 capabilities on a 12-core machine. So you can see that instructions massively increases in the old version, and it stays pretty flat in the new version. And total CPU seconds shows approximately the same kind of shape. Total wall seconds is the stopwatch time. So it's much the same as the cores increase. The new version wins a little bit, but it's not dramatic. You might think, well, if it's not faster. But the thing is that CPU seconds is really measuring the energy cost. It's kind of almost the carbon footprint even. So this is really about making Haskell programs more efficient. And even if they're not faster by measuring it, they're using less resources, so we can do other things at the same time. I've also got here the max pause. So this is a little bit of a dubious statistic, looking at the maximum pause for a given run and then averaging it over 5 times. But you can see that it does marginally get better. It's about half what the old version is for these larger core counts. Yeah. So what's the change? It's essentially taking calls to shed yield out of the hot path. Shed yield, very briefly, is a Linux system call. It's implemented in kernel/shed/fair.c. And this is an excerpt from the man page telling us that the way that we were using it is not really how it's supposed to be used, and it's going to cause problems. Shed yield, the idea is that you don't want to do anything right now, so you just tell the operating system to run something else for a little while. But in practice, on multi-core machines, either you have something in the run queue, in which case when you call shed yield, you're forfeiting your time slice, and so you're effectively lowering your priority. Or if there's nothing else in that run queue on that core, then it's just a busy spin. And that's why we see those high CPU times, is because we've just got a lot of busy spinning going on. GHC itself invokes other processes like assemblers and linkers. So for that reason, the behavior we see in GHC is a little bit different to what we see in a more of a micro benchmark, where we're doing our best to keep the whole machine silent. So when the whole machine is silent, this is kind of the best case for shed yield. And it's why it's quite a difficult thing to measure. Why do we use shed yield? Well, there's various synchronization points in the garbage collector. So when we start garbage collecting, everything has to, maybe I can actually go here. So when we start a garbage collection, there's a synchronization point to make sure everyone's there. And then there's another synchronization point once the leader has finished doing its initialization. Then there's another synchronization point when everyone's finished. Then the GC leader does some cleanup, and there's another synchronization point, and everything can continue running in the mutator, doing things that matter. And at all of these synchronization points, prior to my change, we're doing a shed yield busy wait. So we say, are we ready to go yet? No, otherwise, okay, we'll yield. And so the change is we don't do that anymore, and we use mutexes and condition variables. Yeah, I've done that. So we need to be careful. Like, it's really tricky, the C code and the RTS. And so we want to make sure that we're not causing any problems, get all kinds of seg faults. So there's some fairly straightforward invariants that we can identify, and then they're maintained before the change, they're maintained after the change. We can tell because we put some assert statements and things, so it's going to blow up if anything we think should be the case isn't the case. And then we minimize broadcasting on condition variables. So we'd prefer to wake up one thread than to wake up all the threads that are waiting on a thing. That causes what's called thundering herd problems, where you have many threads starting up at the same time. There's 3 places. So there's the GC entry and the GC exit, and then there's also the work stealing loop. So that's where the GC threads are looking for more work to do. Yeah, so this is describing here, I went through this before, it's describing the invariants for the startup and the shutdown of the GC. And so these are the same, they haven't changed. It's just a different mechanism of doing this blocking. When it comes to work stealing, so what we do is we track the number of threads that are currently working in a global variable. And threads that aren't working are in this wait state, waiting for new work to arrive. And then when the number of threads running reaches 0, that's our stop condition. That's how we know to proceed to the exit of the GC. The tricky thing here is that there are many, many blocks made available for workers to work on during a GC, and we don't really want to we'd like to minimize the number of syscalls we make. So what we do is we just signal this condition variable so that a single thread wakes up, and we only do it when the number of running threads is less than all of them. So that's going to mean that most of the time all the threads are running and we're not going to signal. And when we do signal, we just signal one thread to wake up. And if there's more work and more threads waiting, then there's going to be another block soon, which is going to signal and wake up another thread to get going. So this is showing how much thread yield is being called on the baseline and in the no-spin GC version. So in the top row here, this is the number of times that mutt spin yield. So this is measured. This is one of the synchronization points. This is another synchronization point. You can see it's in the order of 10 to the 9. Notice the log scale here. So like 1 billion calls over the building of Cabal, and then a little bit less for this synchronization point, but again, loads. There's no orange line here because we don't do this anymore. I guess we could be measuring how many times we're waiting on the condition variable, but we're not. So that's why there's no orange line. Any work, here we are measuring how many times we wait on the condition variable. So you can see it's the order of 10,000, whereas before we were yielding 10 billion. These other 4 are spin locks that remain in the RTS. So this one, yeah, some various points. You can see this one's at 10,000. This one's at 1,000, but it's a lot less than these. So it's not clear how urgent removing these is. It probably would not be noticeable, but one might like to do it anyway. And yeah, next thing is, this is an experiment that I did running stress NG in the background while we're running these programs. Stress NG, it's a program just for stressing your CPU. So this is the invocation here. And this is telling it to run one instance on every core to just compute the Ackermann function and try to keep the CPU load of 40%. And then these dotted lines are what's happening in the when you've got this with background noise going. On this axis here, we have the few different programs. So this is build Cabal, which is the one that we've been looking at. And then Coins, Minimax, and Ray are all programs from the parallel suite of NoFib. And the really interesting thing is right here. So the CPU seconds for build Cabal is it's a different mode to these other ones. Whereas before, there's very, very little change when moving to the no-spin GC. But the background introduces this large change, whereas we've already got a change here even without the background for building Cabal with GHC, and that's because of the assembler and the linkers that are running. So this is because GHC never, with assemblers and linkers anyway, it never runs on a quiet box. And then I've also got the total wall seconds here. You can see that gets pretty bad with something in the background. And then this is the average pause in generation 0. So this is the latency limit of your program. And you can see that even with a busy box, we're still maintaining good latencies here. And I mean, in this program, even it was degrading here, wasn't it? Next thing, what's next? There are some schedules calls remaining. It'd be nice to get rid of them completely. Benchmarking on other platforms is quite important. I appreciate some help with this one, if anyone's got a box lying around. And there's an opportunity here to make Cabal and Stack install large sets of dependencies faster by allowing the individual packages to compile with multiple capabilities and some kind of cooperative sharing between them. Potentially something like a GNU job server. I have a draft patch that does that, but it doesn't look that great yet. And then here's some links. So the code for the presentation and all the experiments is available here at GitHub.org GHC bench slides. All of the graphs you've seen have been generated. Baseline it was the tip of 9.2 when I did it. With all of my changes reverted, and then I unrevert. This no any work is with just the work stealing in place. That's not present on any of the graphs, just to make things simpler. And then this no spin GC is with the entry and exit of GC done as well, and also a single bug fix. Yeah, so thanks. That's what I've done. Anyone have any questions for that?
Yeah, thanks for the great talk, Douglas. And I'm now going to bring one question to the stage. And I'm also going to invite Andres to the stage. So the question is for Andres, and he asks, is compiling Cabal the only workload that you have looked at? I saw a comment by Simon Marlowe being worried about the impact of these changes on some no-fib benchmarks.
No, it's not the only workload I've looked at. It is the main one. The NoFib changes, I posted some data where I had mixed up my core counts. So I had some numbers that look pretty bad. The NoFib mostly doesn't change very much. It's not so easy to see on this graph, but these are 3 of the parallel programs. But the building Cabal is the only large workload I've tested it with.
So we currently can't see your screen anymore because the question is on the screen.
Oh.
Because you said you referenced the graph that was not visible anymore.
Oh, can you see it now?
How about
Yes.
now?
Yeah. So I'm not. I haven't really seen any regressions in NoFib from this.
For compile time or for runtime?
Only for runtime. I haven't looked at compile time.
Okay. I just saw the comment on the ticket, and the ticket is still open. So maybe, like as a GHC dev, right, we always like to see if there was a confusion and you have new data on NoFib where nothing much changes, just be explicit about that.
Yeah, I've been kind of focusing on getting the talk ready, but the I'll post some more data on there. Yeah.
Yeah, and those are some really great changes. So can't be overstated, I think. Good to see that they hold up. If you say no, I don't think we would expect NoFib to change very much. So because this is all about GC performance, and there's very few GC heavy benchmarks.
Yeah,
and I'm not sure if there are parallel GC heavy benchmarks in NoFib. Really.
The parallel suite is, I think, supposed to run in parallel, but even that it uses a lot of sparks, and I'm not. Yeah, I don't quite understand how this. There's some complication there because they're treated differently in the garbage collector, I think.
Yeah, and I think they're also not very GC heavy.
No, they're not.
If you improve the GC performance by 10%, which is huge for some workloads, and those have a productivity of 80%, right? Then you get like 2%. So still good, but yeah, that's all about my question so far.
Yeah, thank you, Andres. I'm now going to politely remove you from the stage. If people have more questions, please ask it in the QA tab or raise your hand. So one question I have is, so the whole area of garbage collection has been like intensively started for like decades.
Mm-hmm.
And then why do you see there are still optimization opportunities for like a specific implementation like GHC?
I'm sorry, can you repeat the question? I don't know. I didn't hear the last sentence.
The question is, so the whole area on garbage collection has been like intensively started for decades. And why there are still optimization opportunities in a real world implementation like GHC?
Well, I don't think people look at it very much. So the things that I changed, they were put in place about 15 years ago, I think. I think that's right. And things were a bit different then. Multi-core was less of a thing, and operating systems were a bit less sophisticated. And the glibc implementation of the mutex and condition variable primitives was also less sophisticated. And we have the futex system called it. I mean, it has been around forever. I don't know exactly how long it's been around. This is really not a leap forward in how to implement garbage collectors, or from a theoretical or algorithmic point of view. It's just an implementation improvement, really. And I think there are things remaining to be done as well that, I think that not a lot of effort gets put into improving them.
So I think we need like more manpower in looking at the garbage collection, and maybe there are still like further optimization opportunities.
I think that there are further optimization opportunities that manpower could help. I mean, I don't know if it's the best place to put that manpower, but yeah, like for example, I think that we can do a lot better prefetching when we're scavenging and evacuating.
And address in the chat. Yeah. Would you like to repeat the comment, or I can read it for you?
I can do it. I will paraphrase it. So I think in general, like GHC attracts very contributors that are focused on the type system and the high-level features. And so that means there are not a lot of people, few people that contribute to the runtime system and to the code generation. And there has been a lot of research in LLVM, in the Go runtime and things like that, where I think you can basically pick a paper and look at GHC and say, I can do that there as well. And I've done, like Douglas did some things there, right? Like I've did similar things in the code generation side. Ben Gimari, I don't think he's here, but he did a garbage collector. And like I think there's lots of things that are similar nature that could be done. And if someone is interested, like for research or like personal interest, it's definitely worth having a look there. And
yeah.
Cool. I guess that's all for all the questions. So thank you again, Douglas, for this great talk.
Thank you.
Yeah, so now we are done with our first session. So thanks everyone for joining this session. In around 40 minutes, we will have our keynote given by Martin Agren, and we are going to take a break now. So for people who are on AirMeet and would like to stay for more discussion, please feel free to hang out in the lounge. When the session resumes, you will receive a notification from AirMeet. So thanks everyone, and I will see you in the next session.